this session. Our first speaker is Mykhailyna Bondarenko, and she'll be talking about the sufficiency and conjecturing zero formal ATPs, whatever ATP means for us. I believe Mykhailyna will tell us. Okay, Mykhailyna, the floor is yours, please go ahead.
Okay, thank you. So, first of all, let's acknowledge the amazing help of my supervisor, Mr. Lukashenko, who's been meeting with me every week for the last half a year and helped me a lot on this project. And a short plan, I will explain the context as pointed out earlier. Motivation, outcomes, research questions, planned approach, and evaluation plan as of the time of the writing of this expose. So what's the context? So first of all, what are ATPs, right? So ATPs are automatic theorem provers, right? So we have mathematical theorems and we want to prove them automatically. But there are two ways you can prove theorems, right? There's the informal approach and there's the formal approach. So what are the informal proofs? So informal proofs are proofs that we are all used to. They're written in natural language, and sometimes they do rely on our human intuition, on like obviously assumptions, etc. In contrast, formal proofs are proofs that can be checked by an ITP, so interactive theorem provers. These look like code in a special programming language. And if they compile, then the proof is complete. If they don't compile, then there is some fault in your proof. And they're usually based on some axiomatic basis. For example, Lean4 is based on type theory. Okay, so first of all, what's the motivation for studying automatic theorem provers? But first of all, they are right now at an inflection point, right? So if you look at the benchmark, this was considered like a really complex benchmark just a year ago, with the best result being 8 out of 672 problems solved. But in the last year, the performance of this benchmark has improved to almost full saturation, right? So this is the progress we're seeing right now with automatic theorem proving, to like put you in the context of this benchmark. These are the problems from the Putnam competition, which is a competition, it's like an Olympiad for undergraduate level mathematical students. Really complex, really hard to prove all of the answers there, but we are getting there with AI. However, there are two critical gaps in the current approaches. First is efficiency, second is conjecturing. What is conjecturing? Conjecturing is coming up with the answer, right? So when you're proving something, you're proving a statement that already exists. When you're conjecturing, you're coming up with the statement itself. So what's the research goal? The research goal is to address these two gaps. The efficiency you want to address by improving the open source prover models, LLMs. And the conjecturing we want to address by implementing the full coming up with the answer and proving pipeline and using the disprove feedback for enhancing our answer. Okay, so let's look at the related work for a short time. So there have been the following approaches seen in the most modern formal provers. So the first is to auto-formalize for dataset generation. So we have informal proofs, and then we formalize them into a programming language, right? So like Lean4 and ITP. And then we use this dataset for training a prover. The next is agentic decomposition. So we decompose the problem into its subparts. Next is verified various repairs. So we use the feedback on what's wrong with our problem currently, why doesn't it compile, to enhance our proof, and also reinforcement learning, and finally conjecturing. Conjecturing has mostly been used to augment the data sets, right? So we have some statements already, but we want to, for example, make them simpler, make them harder, or maybe use test time reinforcement learning as an alpha proof to augment, to like basically fine-tune our model for the exact problem we are tackling right now. Okay, so the first problem is the efficiency problem. So the efficiency problem is seen really clearly, right? So if you look at our prover, which achieved 668 out of 672 problems on Putnam bench, it uses up to $1,400 per problem, which is like really much, right? It also uses large closed source models, right? So we don't have access to all of its code. If we look at the best open source model, which is the Galo Prover 32 billion, it still achieves an accuracy of 86 problems, right? The goal for this research would be to enhance the best performance of an open source for LLM that doesn't rely on closed source models and is much cheaper, right? So the second gap is conjecturing gap. Right now, the Putnam competition, the one that is now saturated, is there are like two splits here, right? You can see with answer and no answer. And so the with answer is now saturated, but the no answer split has no submissions at all, which is concerning, right? What is the difference? So in the first split, we're proving we have the statement that contains the answer, right? And in the second split, we don't have the answer. We have to come up with the answer, and then we have to prove the answer, right? And there's also limited power work in this direction. Yeah. Okay. How would we tackle this? How would we tackle conjecturing? So the idea is that we would use the feedback of the prover model to enhance our answers, right? So if we came up with a correct answer, we can prove that it's correct, right? We can verify that it's correct with the prover, and then we have this feedback, and we can go on, basically move on. If we prove that the answer is not correct, we come up with a counterexample. This serves as a really, really strong feedback signal for our answer searching agent, right, to improve the answer. Right? What are the best conjecturing agents right now? If you look at the IMO 3 competition, which is an informal competition, right? It has informal problems. The best model there right now, the best model that we have access to, it just does ensembling, right? So it has a simple ChatGPT 120 billion model that has tool integrated reasoning. It comes up with the answer, and just we run this 8 times, and we pick the majority answer, right, and regulate it. So this is really followable, as we'll see later. Okay, so the first research question is that can we improve the efficiency of the provers, right? The second research question is, can we actually achieve like viable conjecturing, as I talked about earlier? And the third research question is that, can we use formal feedback from proving or disproving a conjecture to improve the conjecture? Okay, so what's the methodology? Methodology is really simple here. We establish a baseline, we evaluate we evaluate our pipeline, and then we refine it, and then we go on to improve the results, right? What we accept here is what we want here is to make the cost of inference go down and maybe even improve the accuracy, right, of the provers and conjectures. Okay, so what's our approach on the efficiency track? So there are multiple things we can try here. We can fine-tune the models for specific areas of math with LoRa, or maybe even do representation levels sparse autoencoder steering. We can do chain of thought or tactic pruning to help with the token budget, because, for example, the Gödel prover, it has a context limit of 40,000, which is quite short, right? It doesn't allow us to fit in out of the self-correction turns. Yeah, we want to maybe extract goals, right? So it simplify the problem, as we talked about earlier, with the Hilbert approach, but do it here. Yeah, so basically, if what is the success criterion for all these approaches? The success criterion is that we match or reduce exceeded baseline, or match or exceed baseline, or we reduce per cost. Okay, for the conjecturing, right, for the formal proof-disprove feedback loop, we have 2 parts of this, right, 2 variants of this. The first is the informal setting, for example, IMO3, where we don't have a formalized problem. The second setting is where we have a formalized problem. So this first step is optional, right? So we first can formalize the problem, right? But if we have the formalized problem, we skip the step. When we have a formalized problem, we generate an answer with an agent, right? So we can use tool integrated reasoning. We can add like tools like Lean4 to there. And then we auto-formalize the answer. Then after we have the answer, we can ask the prover to prove or disprove this answer, or maybe come up with a counterexample, which is a separate kind of task. And if we have a counterexample, we have like a really strong signal to revise the conjecture that we have came up with. Okay, so what's the evaluation plan? There are multiple benchmarks available. Only some of them, like one-dimensional answer, has the split for us to work with conjecturing, but like some of the benchmarks like mini F2F can be transformed to make them into no-answer benchmarks. Right, we also have informal benchmarks like IMO3. Let's look at our early experiments as of January. The first experiment is that the like model that has won the first IMO competition, right? So right now we have the third one, but the model that has won the first one doesn't solve any problems on the third one, right? So it solves 0 problems. And the pitfalls that we have detected is that so this is a tool integrated model, right? So it does Python calls, but instead of doing like logical reasoning and then running Python code that is feasible, right? That will finish in time. It's really really frequently delegates reasoning to brute force code, and when the code fails, when we like even prompt it to not brute force, it still does brute force, and it just reduces the number of iterations, and the answers that it comes up with are wrong. And when we try the most modern approach to this, like the leading approach right now, what are the problems? Actually, there are less problems, much less problems, because we solve 9 out of 10 reference problems on IMO3. But however, like this experiment actually shows us it exemplifies the need for some kind of feedback, because for several problems, yes, we do come up with a great, a fast consensus, right? We have the answer, the correct answer, but for the other problems, okay, sorry, this should have yes, 3 problems. We have more attempts, and sometimes the decision boundary is fragile, right? So there are the wrong attempts, that incorrect answers, they cluster, and the ensembling it is fallable, right? So it is a good signal, but it is fallable, and if we can make improve this in such a way that formal feedback will help us find the correct answers better, then it would be great and amazing. Okay, so main first proposed contribution here in this whole work is that we use formal proving or disproving or counterexamples to refine their conjectures, right? And we also address the efficiency gap in the provers. Okay, thank you.
Thank you very much. Do we have questions? Yes, please.
A quick question. The nominal math model, on which year is it from?
It is from, I think, 2 years ago. Yeah, so it won the first competition. Right now it's the third competition. The competitions happen almost every year, like less than every year, I think. Yeah.
More questions?
We understand correctly that actually this framework is pretty flexible, for example, to inject a human in the loop instead of automatically generating some conjunction. We can take, for example, something that was started by the human, but human got stuck, and we can iterate like that, right?
Yeah, so the reason that we are developing these automatic theorem provers right now is that like to formalize math is a really complex and time-consuming task, right? So we had to invent whole operations to organize people to prove like one theorem. We have to build this baseline on theorems to prove some theorems, right? And to automate this would be great because sometimes maybe we can come up with like a baseline proof. Maybe it will be a complex and long proof, but we'll be able to come up with a baseline proof automatically and help humans formalize math.
And also another question is, for example, in this iterative framework, the conjecture is evaluated just by saying one like hard labeling, correct, not correct, or have you considered maybe something like soft labeling, or is it possible? So this is partially correct, or something like that.
That's a good question. I haven't considered that because you're correct that sometimes like a problem can have three answers and maybe the model came up with only one answer. But when we have this disproof feedback, in the disproof or in the counter example, we would see that the model missed some of the answers, right? And so this will be the soft feedback that you're talking about.
And follow-up question: do you feed kind of the whole loop context into the model, or for example, how the iteration is done? We have a first conjecture, we evaluated it, it is okay or not okay. Like we ask a model to generate a new or new based on this existing one. How this?
Yeah, so the context is really important here. However, like because of the context limits, it is important to try to like compress the context, right? So like to not give the whole chain of thoughts to the model, but to give just the previous conjecture, the feedback, and maybe try to improve this conjecture with this feedback. Yeah.
Maybe it's worth considering somehow aggregating or what is like standard number of iterations? Is it infinite number, or is it, let's say, have some finite number, say let's do 5 iteration, or how do you see it?
So for example, if we take Gödel prover, which is the leading open source prover right now, it is limited to 2 turns, right? So it generates a proof. If the proof is incorrect, then it tries to generate it once more and then once more, right? So this is limited by the context of the baseline model. So the Gödel prover is a fine tune of Quen 3, Quen 2.5 even, I believe. And the Quen 2.5 has a context limit of 40,000, right? So that's why you can fit in more turns. But what we have tried actually, like in the future after this expose, is to, like one of the approaches we have to try is to remove maybe the chain of thoughts, maybe to remove some unused conjectures in the proof, to try to compress this context and maybe fit on more turns.
Okay, so final question from my side. During this work, like, have you spotted something interesting that, for example, you got yourself thinking, wow, this is really interesting result, it proves, or like, have you experienced like aha moment or something like that?
Yeah, actually, yes, because one of the most surprising things was that, like, again, after this, when we started working on conjecturing, the accuracy was pretty high, right? So right now we are at a point where we have created conjectures on Putnam bench, we have formalized them, and even if we do exact string match, which is like really low heuristic, right? Because you can write 1, you can write 2 plus 2, sorry, you can write 2, you can write 1 plus 1, and this would be the same answer, but right, we are checking the exact string match. Even in this case, we have 30% accuracy, right? If we, like, we will proceed with trying to check answer equivalence in a more sophisticated manner. But if we use an agent to try to check answer equivalence without trying to formally check it, right? If we check it informally, the pass for accuracy for conjectures on Putnam bench reaches 90%. This is really high. This is like, and I'm surprised that the leaderboards right now is completely empty, right? We could be the first ones here, but we will see.
Okay, more questions? No, we have no time for more questions, so thank you. So, our next speaker is Bohdan with Yuriy Pryyma. He will speak about routing common circles with the reinforcement learning. Bohdan, the floor is yours.
Yeah, okay. Should I run my microphone or use this one?
Yes.
Okay. Yeah. Hi everyone, my name is Bohdan, and I will talking about routing quantum circuit-based reinforcement learning. I work on this project with Yuriy Pryyma, who is a lead engineer in the Ukrainian startup that work on quantum computers. And my plan will be following. Firstly, I will talk about problem description, then about our motivation why we decide to use this problem, and then we will talk about related ports and research gaps, approach to the problem and evaluation metrics, then evaluation results and the future work. Let's first start with problem description. The problem is that modern quantum computers are not directly connected with, not all qubits are directly connected with each other. For example, in this case, we have the qubit 1 and qubit 12 that are not connected. But in real life problems, we need these qubits to communicate. And to do this, we are using the swap operations that are working like following. The first one, we are using swap operation between the qubit 1 and qubit 4. And the next, we will use the same swap operation between qubit 1 and qubit 10. And now we have the direct connection between the first qubit and the 12th qubit, which means that we can now use our operations, we can run our operation. The motivation is that, as I said, the hardware constraints that not all qubits are not directly connected. The second problem that the solution for this problem is NP hard, which means that we couldn't find a correct solution in feasible time. But the third problem is error reduction. Each operation, this problem is that modern quantum computers are noisy, and each operation is could lead to the error. So using additional swap operation means that we could receive a bigger error, and this will be bad for our model. The last one is resource optimization. The lower number of swap operation will reduce the total time of executing. So our research goal is to create a reinforcement learning environment and the models that could work with on this problem. The second is to compare results with Cyber algorithm. The Cyber algorithm is a state-of-the-art solution that not use reinforcement learning. And so compare our results with it will show that if our model is good enough. And the third, and maybe the main, is to create the models that could work on different topologies. And because, as I will show in related works, most modern solutions are trained for specific topology. So our related works, first is a classical algorithm, as I said, is stochastic swap, nearest neighbor, and the cyber, which is state-of-the-art. And reinforcement learning, that could be alpha router or quantum circuit trust building with reinforcement learning. And let's start with cyber. It is like something similar to a greedy algorithm, and it uses forward and backward passes to improve its accuracy. And it iteratively improves its own solution. The next one is AlphaRouter. This is a model presented by Google, and they trained a model on a few topologies to show that the multi-color approach and transformer could solve this problem as well. The model, as I said, was trained specifically for specific topology. This is a problem of the solution, which means that when we even small changes to the topology will lead to the impossible to return the model. The idea that was sparked from there is first of all, it's reward function. Also, same model, it consists of one convolution layer and two linear layers. So it's quite simple, and as I said, it could not be adapted to different topologies. And here is the results of same model. In the first column, we could see time, and in the second is swap. As we could see that the number is 1, 10, or 100 is number of Monte Carlo iterations. So we could see that their results are better than swap, but which means that the solution is correct. And what is the research gap? The classical algorithm results are not so good, as we see that reinforcement results could be better. The second one is the reinforcement learning algorithms. They require time to train a specific topology. For example, the AlphaRouter needs 3 days on a GPU to be trained for specific topology, which is too much when we want to train hundreds or thousands of topologies to understand which one is better. And our approach is following. We want to create the environment. Then we will simulate circuits and topology and create a reward function. It will be following. We will give a small negative reward for each swap operation. So this will lead our model to reduce number of swap operations. Also, we will give a small positive reward for each step taken on the circuit. This is required to reduce model. It is like a small reward to improve training. And the last one is large positive reward for completing circuit, which means that we solve our problem, so we will reward a big reward. And there is also a negative reward for cycle in topologies. We add this reward because our model during training receive a lot of cycles, so we decided to fight with it by adding large negative reward. As a model is first of all, is create the model that was presented in previous form, like AlphaRouter, and the second is graph neural network. I will talk about it later. And then evaluate our model. So this is our approach. Evaluation mathematics, it is quite simple. We will calculate number of sub operation, and the lower number means the better results. And also we will calculate training time just to understand how good our model and could we use it in real life. So about early results, we already create the environment that is fully sophisticated and also create the models that the graph neural network, which also give a good results. I will talk about them later. And the last one is adapt model based on results. Yes, that's also we do. We update our graph network to improve the accuracy, and also what is in the progress is training process adaptation. So we want to adapt our training process. I will talk about it later. So about encoding for our model, first of all, it's node encoding. We will use each connection as a separate node, not qubits as nodes, but connections. For example, in this case, we have connection between copy 0 and copy 1. So this is our node. Each node consists of few operations. The operations is data that we should solve. This is encoding for, I will also talk about later. And also MSCA used to add node information. So it is random walk that give us a better information about node and often used in graphs. And the edge encoding, we have that if two connections has shared qubits, they connected. For example, in this case, qubit 1 is shared for connection 0, 1, 1, 2, and 1, 4. the operation encoding. This is why we need to cooperate between two qubits. For example, as I told earlier, between qubit 1 and qubit 12, we encode the distance from first qubit to our node, the distance from second qubit to our node. Also, we give information that if it is possible to do our this operation at the moment, and is there how many other operations this operation work, and the total distance between first and second qubit. This and all this is normalized by graph geometry. The model is looking in the following. We have input layer, and then we have two graph layers. The first one is local, and the second is local. The local model is working on a specific operation, but the second model is consists to work on communication between these operations. So we choose and the training processor will be following. We generate random circuit, evaluate model, and increase complexity if our model is already trained enough. Here we could see the architecture. We have the first model that encode operation, and the second, the global models that communicate calculate communication between operations, and then we combine the results. And the last one is here's our results. In this case, we could see the first three model was trained on first three results was trained on one model with less than 12 qubits, and Orons is the algorithm, the topology that was used in train, and we could see that our model received even better results than Saber. While Casablanca is the model, the topology that was not provided in training dataset, and our model received a little bit the worse results. And also we trained Guadalupe is another 16-qubit operation, and we could see that our model isn't trained enough, but as I said, we trained it only with topologies for less than 12 qubit. So when we receive 16-qubit schema, it is expected that we don't receive good results. And the last one is Melbourne. This is another case, as we train the model for one specific topology, just to prove that that our model works correctly. And we could see that our results are better than Saber. And we could also compare it with the results given in Alpha Router for topology 12O, which is quite similar to Melbourne. And yes, I receive results 24 operations, while we receive results 24.4. So yes, that's quite well for us. And the future work is, as I said, is to update our training process. We want our model to use Cyber for training and adapt our training process by giving information by using Cyber as a learner for our model. That's all.
Thank you. Questions, please.
I think so.
Oh, yeah. Also,
It's usually greatly all support which is provided by Yuriy Pryyma, and it's difficult to understand, but this is still want to verify. On the slides with your earlier results, I saw metrics, providers, and the solution, but I didn't get what kind of metric it is.
Yeah, this is a number of swap operations needed to solve the problem.
Okay, and it's also used as one of the required parts.
Yes, it used.
Okay. It also, maybe I didn't understand in context of this domain. What is policy optimization for such clients and this domain? How it works? Because for some typical stuff, you use some PPO or...
Yeah, we use PPO. We are also using PPO for training, and yeah, here is a few. Oh, yeah, just a second. Oh, Yeah, here is the reward function. So we give negative reward for each swap operation. By giving this reward, we are reducing the total number of swap operations needed to solve this problem. So model understands that we need to minimize this number.
Okay. Do you consider to try other policy optimization?
Yeah, we are working on implementation cyber algorithm as library. So we could know that by using this approach, we could know when we are working moving to the correct path or incorrect. If after we make some operation, the number of operations needed to solve in cyber also reduced. This means that we are working in the correct direction.
Okay. That's all from my side. Good luck.
Thank you. More questions? Was that a question? No, no, someone. No, greeting. Yeah. So I have two questions.
Okay.
First question is on topologies. In the results table, you mentioned
Is this?
four topologies, as far as I understand. So Casablanca regions and Orins, Guadeloupe number are different topologies.
Yes, they are all
And
different.
those topologies are fixed.
Yes, they are fixed.
So you have no possibility to alter any topology. You just use one to solve the task. So it's a meta parameter for the task. Isn't it?
Yes, yes.
Okay.
So in this case, we like use Casablanca and other model or Orange and other models for training, and Casablanca doesn't appear in training process, so our model doesn't see it before, and this is result without any training process.
Therefore, it failed miserably.
Yeah.
Okay. My second question is related to the relationship between our model and the Sabre.
Yes.
I've just looked at the reviewers comments for your paper and the answer. How did you improve your paper? Could you please comment on the reviewers comment and the report?
Yeah, first of all, when we are working with, when we writing this article for Symposium, we are using only one global model to interact. And when training, we didn't receive as good result as expected. So we decided to add this local model, which was trained on specific operation. By giving this model, we like improve accuracy because we give more information about each operation. Model better understand when to work, how to work. And by adding this new local model, we improve our accuracy.
Okay, this is your answer to the comments by reviewer too, I had.
Yeah, both reviewers write about accuracy.
Okay. They had some more comments.
Um,
You don't remember?
Yeah, I don't remember exactly. Yeah, there was some comparison because about accuracy, and there was one, and also there was comments about that we should we use should we try could we like use these results in real life, and because this is quantum computers, and of course we couldn't test our model on quantum computers. But because we use simulations provided by IBM, we could simulate some quantum computer work using the classic computers. So these results are mostly similar to the ones that will be on the quantum computer.
How much mostly is mostly?
Like I think 98% accuracy or something like that.
That's a very bold statement
Yeah.
if you're in quantum computing. Do you know about the degree of repeatedness in quantum computing branch of
Yes,
science?
the degree of repeatedness is, if I remember correctly, is the number how many times.
How many times when you repeat the experiment you get the same result?
Yes.
So
And well, that's a hard question because in this case we are working on communication between qubits, and we don't need to know information about how the quantum computer will work, but because in any way we need to create these operations, and our task is to reduce the error, the total error, by reducing number of swap operations. So we don't work on the quantum computers, but works on the hardware, software part to improve their accuracy.
So the software does not need to know how a quantum computer works.
In this particular problem, not always.
Okay. Okay. Thank you very much. Yep, we're exactly on time. Thank you. So, next speaker. Just give me a second. Our next speaker is Anastasiia Mazur, lightweight recurrent architectures, low resource multimodal applications. So Anastasiia, the floor is yours, please go ahead.
I'm really trying to understand how to
To
present you the presenter view correctly without the presenter notes.
yes. You need notes.
No.
We don't. We definitely do not need the notes.
Я зашила его полностью просто.
Так, так, так.
Що ж, будемо по пам'яті. Та що ж таке? Зараз, секундочку. Якщо щось може піти не так, то воно піде не так.
Actually, do that next. You have to share a window, not a full screen.
Sorry, Dad. Sorry, I'm not very good with computer sections.
Okay,
Yes.
wonderful.
So, hi, my name is Anastasiia Mazur, and today I will present my master thesis exposé called Lightweight Recurrent Architectures for Low-Result Multimodal Applications. That's why I need notes, because I can't remember my own title. And this work investigates whether the model linear time sequence models can serve as practical and efficient performance as transformer-heavy ones. We will talk about the exact motivation, the background, and related work. Then we will go to the research question and my hypothesis. We'll review the already existing methodologies and research plan we are following for now. And then I will share with you the early results and the progress we have and make some conclusions. So, the exact motivation is very simple. So multimodality models are very powerful, but also expensive. When a model processes audio or images and text together, it faces a big problem. For example, a 30-second audio clip might produce thousands of spectrograms tokens, and a high-resolution image can produce hundreds of thousands tokens to process. And in standard transformers, we know that the self-attention cost grows quadratically. And this becomes critical in lower resource settings or other languages like Ukrainian language, or for just small phased areas. We have to make the researches and deployment with less compute budgets, know the data set, and deploy on commodity GPUs or even edge devices. In these scenarios, compute overhead is not only the small inconvenience, it directly limits which experiments we can run, what we can deploy, and what context line we can afford. So efficiency actually becomes a prerequisite for making low-resource multimodal research vital and valuable at all. The background from this work comes from the resurgence and renaissance of linear time sequence models and RNNs itself. The first family is linear attention and retention. Works like the linear attention show that part of attention can be easily linearized and written as an RNN update, enabling all out of an complexity and computational inference. The performer model approximates the attention with random features. RedNet, on the other hand, introduced a retention operator that supports parallel training, but switches the recurrence and chunk-wise for the inference for the test time. And flying from work, one of the most beautiful mathematically version from last year extends this to bidirectional settings, which is critical for encoders to understand the local context better. The second family is a state space model, the well-known Mamba, a new version of it, showed that structure state dynamics with careful parameterization can model very long sequence efficiently and be weaker and more memory efficient than transformers. Mamba aided input-dependent selectivity and demonstrated strong results with fast inference. For vision, the researchers already applied 2D scanning strategies to convert images into grids and sequences that can be processed by the state space architecture and mathematical theory. And the third family is recurrent token mixing, exemplified by RWKV family. They also have the improvements from different researchers. For example, Vision RWKV adapts the images using spatial shifts to adapt it to local context. And this is very same idea as Mamba scanning patterns. Audio RWKV handles spectrograms with bidirectionality recurrence, and this is very similar idea to the line I showed you previously. And RWKV clip even shows that a recurrent backbone can be driven as contrastive vision language learning. What's important about all these three approaches that they all offer linear complexity, but differ in how they handle global context, locality, and cross-modal fusion. So that's why we face the main research gaps. First is entangled design choices. Current multimodal applications combine multiple mechanisms at once, and it makes very difficult to understand which component is actually responsible for the performance. We cannot currently isolate causal contributions to efficiency or quality. The second one is inconsistent comparison. The literature is fragmented. The tasks are extremely different, the benchmarks too. So some papers only report task metrics without runtime profiling, while others can report the speed up, but they just don't use controlled benchmarks, so you cannot prove it by yourself. And the third one is actually low research settings. Most of the time, the papers are written on big scales, big data sets, and for example, using the latest RWKV7 model that was prepared for the adoption of large language models, which is not applicable to the conditions when we have only 2-3 GPUs for our development or research. So this thesis directly targets all three gaps through a unified evaluation harness, controlled ablations, and explicit focus on low resource constraints. It is organized around 5 research questions. The first one, the central one, is undermatched parameter counts and comparable training budgets. Which recurrent family provide the best quality versus efficiency trade-off for speech and multimodal alignment tasks? The second one asks about low research robustness. Which design choice can mitigate the overfitting and training instabilities in low research settings? The third one investigates sequence length sensitivity. Do recurrent backbones shows increasing advantages as sequence grows? Or, for example, are we more efficient on tasks like streaming with short utterances from 1 to 3 milliseconds? This fourth one is mostly deployment focused, which backbone and adaptation strategy gives the best end-to-end backbone profile and convenience to deploy. And fifth one is barely optional because it asks about the recurrent principles, if we can support the generation in diffusion models, and this extends scope, so it's only applicable if all other core questions are answered satisfactorily. The hypotheses we're building the research around are as follows. The first one is priority improvement under constraint, so I expect that at least one model recurrent family will match or closely approach transforming baselines and task quality at comparable parameter counts. The second one, the efficiency gains of recurrent backbones should become more pronounced and sequence grows. The third one is that I expect that applying just small adapters or over adapters to recurrent models will produce more stable training and better result than full fine-tuning. And fourth one is the backbone objective iteration. I expect that optimal recurrent family will differ by task. For example, the architectures that were optimized for tabular structure will be more applicable to the ACR speech recognition task, when architectures like last Mamba that better preserve global semantic structure will be more efficient in the image retrieval and alignment task. The approach is very simple. It's mostly about the methodology and fairness of comparison the backbones. It has 3 strategies. The first one is the same modality encoder. The second one is a linear time backbone itself that can be easily switched and have to follow the same parameter and training budget as all other models we compare it with. And the third one is fusion and evaluation, when we test the different fusion and improvement strategies to jointly measure the quality and efficiency. So yeah, the key methodological contribution is just the ablation framework to isolate 6 design dimensions: the type of recurrence, whether gating for fusion is used, whether the model is bidirectional or causal itself, how the 2D context and local context is injected into special inputs, and the fusion strategy itself, so that make the comparison fair enough. We focus on 2 main tasks and regimes. The first one is a low resource speech recognition with audio understanding. Here the challenge is long temporal sequences from spectrograms, a very short one. And the second one is vision language representation and retrieval. And here the challenge is the dense visual token grids from image encoders. And the problem is understanding the local context better or as efficient as transformer do at the same parameter budget. Research plan also follows. Now we are on the end of the March stage, so we already implemented the baseline adapters and fusion strategies, and on the next months we'll just run all prepared backbones and compare them on final benchmarks and in big data sets. The early results were primarily methodological, which was consistent with the project phase, which was when we were reading the expose itself. So the most important finding at those time was the consolidation of shared design space. Throughout the all extended researches and mapping studies, they've used the same idea with different mathematical adaptations, and the problem and the task and challenge was just to understand which one is more unified, versatile, and can be applied easily to all 3 families, so we can reuse it under different constraints and scenarios. The risk of the research contain 4 main points. The first one is optimization stability. Some recurrent and SSM models are just sensitive to numerical precisions. The second one is multimodal generation. It's very fascinating and pretty practical, but it just can take most of the time of the research, so that's why it's optional for now, but still very desirable. The third one is data availability and the benchmark to compare everything within. And the first one is time and compute budget constraints, so running very different ablations with tens of improvements under different constraints is pretty expensive. So sometimes we have to reduce the scope and just remove some ideas because we have no time to run it. So to conclude, This thesis proposes a unified investigation of lightweight recurrent architectures for low result multimodal adaptations. The central thesis is that this model can meaningfully improve the accessibility of multimodal system, and they can enable long-context processing with favorable memory and latency compared to transformers. And the expected deliverables. The unified mathematical benchmark and framework that will suit to most of the tasks and most of the family of models. And the second one is controlled comparison, when we can identify which improvement or which mathematical approximation face which problem and what is the efficiency itself. Thank you.
Thank you very much. Do you have questions? Smart questions?
Why?
Why smart? Okay. Could you please let me start with my questions? Could you please put your presentation back on screen? And when you do that, could you please go forward and go back to the slide where you have your two use cases?
Yeah.
Yeah, speech recognition and vision language retrieval. Are those two really multimodal?
What do you?
I mean, does a speech recognition, how many modalities do you have here?
To the text and the audio itself. But it's
Text in which form? And why?
text.
Why do you need text here?
Because we try to encode the mass spectrum. So the audio is being represented as mass spectrum as an image, actually. And then we try to encode it to the text. The dual test for this is just speech generation from the text.
I'm sorry, text is not the second modality in this case, because the text is the result of your processing. Two modalities appear when you have two inputs, textual input and a spectrograph input.
So actually, the initial idea was to test the speech and vision to show that, yes, we can end up with encoding the text, but we can apply the same architectures and the same kernels of different recurrent families to both the representation as mass spectrogram of audio and the representation of image. And we can apply the same improvements of approximation to handle both of them on the same efficient level. The one idea that is currently out of scope is the diffusion generation, when we also have the adapter with the text. So we can inject the text instruction as long as, for example, some lower adapter with style instruction. So that would be this unified multimodal latent space. That's why I showed you the RWP flip, which was produced to create the contrastive learning to create the same space for different modalities. But it's just not in the main scope. So that's why the multimodality is mostly represented just by two different tasks, but they not combine the two modalities at once in both of them.
I'm sorry, this means that this task A, speech recognition, is not multimodal. It's single model. Similarly to that, vision language retrieval is single model, single modality task. And you have multimodal in your title. Okay. Why do you now think that it's out of scope? You said that multimodality is out of scope. I'm just interpreting what you have said a minute ago.
No, it's not multimodality is out of scope. I just try to show that the framework can be applied to multimodality, but I do not promise that at the end I will show the benchmark result of multimodal tasks. That's why we started from two single modalities, but the different modalities, the audio and the image.
Okay.
Just to prove the hypothesis.
Thank you. More questions? As you wish, because I have, okay, yeah, that's it.
I'm interested in, so you describe the tasks, and what is the data set? Can you name the data set? For each
The
task?
first one that was used for the first testing was the Common Voice, Ukrainian data, 35 hours training data with short utterances from 3 to 10 seconds. Currently, we switched to the bigger ones with 2 and 5 million utterances for these exact tasks. And they are English language because it's more like it's more accessible compared to the Ukrainian language to test it on this.
And
Is English, I'm sorry to interrupt, is English a low resource? Low resource is in your title, isn't it?
The exact title for the diploma work was a little bit changed.
I didn't see it.
So
I just saw the title of your presentation.
yeah, that's why here we use the small low resource data set of Ukrainian language.
I'm sorry, Stanislav, for interrupting.
Oh, it's okay.
Please continue.
yes, and the data set for vision language retrieval.
I don't remember the name. It's just CFAR 100 or something like that, I guess.
Okay.
Finished?
Yes.
I still have a question.
Yeah.
You didn't mention any experiment in your earlier results. Do you have any experimental results right now at this later stage? Could you please elaborate on that? What has been experimented for?
Okay, so the main new findings that on the Common Voice Ukrainian data, currently not tested on bigger data sets, we managed to achieve the same efficiency as accuracy as transformer backbone on RWKV6 kernel with improvements in terms of bidirectionality. The mathematical bidirectionality with applying the bidirectional mask and using the delta delta rule instead of exponential forgetting. So that's the main achievement here. But also all the experiment results were focused on retesting the approaches that were stated in early research. For example, how it reads the local context with 2D scanning or convolutional sheets to refuse the result of them before putting it to the kernel or not. Also, we have the experiments related to inference processing. The causal one, the bidirectional one, the more recurrent one, and chunk-wise in order to speed up the inference itself after we train the model. And also we tested the streaming test and proved that the accuracy of streaming on the short length audio from 1 to 3 milliseconds. The Manva and RWKV backbones with no improvements even, but with applying the carrier state and chunk-wise inference show better accuracy than transformer itself. So that's it.
Thank you very much. This finishes our second section. We are warmly welcome to have some photos and some snacks down there at the coffee.
Wait,
No,
we really have no. We have 7, 2, 3. 3 presenters, 3 talks.
there's anything else. Sorry.
I also would like to have a coffee, but
Okay. Sorry, Oleh. This is your turn. Coffee is, well, rescheduled. Our next speaker is Prostakov, supported by Valeriia Lukashenko. Oleh will be speaking about reconstructing tau leptons on the low tau regime. Well,
figuring out why Gantt does not ethnic screen, but
yes, I'm sorry for mixing tau leptons with coffee.
it's fine.
I can't make it full screen because otherwise Zoom, for whatever reason, just pauses the presentation. So, hi everyone, my name is Oleh, and my thesis project is about applies machine learning to high energy physics to tackle the problem of reconstructing electrons in low-T regime. This project is advised by Valeriia Lukashenko. She's a postdoc researcher at University of Zurich, and we are heavily supported by CMS. We use their datasets. As final large-scale evaluations will be done via their clusters on, once again, the datasets that they provided. To give you, so the talk is structured as follows. We'll start with physical background and motivations behind the project. I will explain what those leptons are and what is the problem of reconstructing them. Then we discuss the problem itself, what is the vision of the solution, and the research plan to achieve it. And finally, we'll finish by discussing early results and sharing what we are to work on in the future. So let's start with basically the background and the particles in question. In particle physics, there is a type of particle named tau leptons. They're produced in decaying chains, in forming collisions, for instance, in Large Hadron Collider, but themselves decay very quickly, well before reaching the actual detector. When decayed, those tau leptons produce 4 pions. They are also particles, and they are more long-lived than tau leptons themselves. 4 charged pions and 1 neutral. They are actually what reaches the detector, and basically how we know that a tau lepton decayed there, because they themselves remain basically invisible. So the problem of reconstructing a tau lepton is basically about finding that exact triplet of pions, and based on the characteristics acted by the detectors, we are able to quite accurately reconstruct the characteristics of the original lepton. Now, low-T regime of my project means that the leptons have very little energy. And following the laws of the energy condensation, dotted pions of that lepton have even fewer energy. And this fact complicates our problem in 2 ways. First, the pions themselves start resembling background noise, which is also low energy and basically acts at random. And the second and even more challenging problem is that they no longer travel together. And we cannot apply usual jet-seeded algorithms that are used at CMS to group them into jets of basically 3 pions. So what it means is that to reconstruct low-PT leptons, we have to take a haystack of detected pions and look for basically 3 needles within that haystack. If we don't find all the 3 needles, we won't be able to reconstruct. If we take different pion as a needle, the reconstruction won't be accurate. One such haystack has roughly 1,200 particles with reaching like up over 3,000 on the extreme end. You can see an example of what the map of the detector looks like with such an event. A lot of blue dots and 3 tiny red dots that we actually want to find. So this project is motivated due to 4 reasons. Low-PT particles are more common than medium and high-PT ones. Just statistically, it's more likely that there are more low-energy particles and fewer high ones. Existing state-of-the-art algorithms usually focus on medium and high PT particles, despite low-PT being more present, being more common, mostly because they are way harder to detect, and because some algorithms that simplify the detection work only medium and high PT regimes. The algorithm that is currently used at CMS for low-PT reconstruction, it was introduced all the way back in 2018, way before a lot of modern machine learning paradigms, way before the rise of transformers, before the widespread application of graph neural networks. And that algorithm that is currently used is not capable of processing very low PT particles. So they themselves have like a hard cut at the lower end of like 0.5 giga electron volts in terms of the particle energy. Whereas the simulation at CMS demonstrates that roughly 50% of ions produced in such low PT events are actually below that cut. So for the problem, we have two objectives here. First one is to beat the existing set of art results on low PT reconstruction. You can see that a lot of like the results here, the signal efficiency represent the portion of events where all the three particles were reconstructed. And on the x-axis, you can see the energy of the particles that produce those ions. What I meant by like very low PT ring is that below like 5 electron volts, we can see that even their production algorithm starts producing kind of poor results. And like for higher low PT spectrum, they also do not score very well, like below 0.5. The second objective is to actually push into that very low PT region inaccessible to the current ATPs model. We expect that it would be possible due to like the more advanced architectures, more advanced training techniques. Those objectives are supported by like three research questions and their hypotheses. The first one is whether or not we can adapt state-of-the-art jet tagging models like particle transformer for the problem of low PT reconstruction. We hypothesize that we can, and that interparticle interactions will help us improve the results. However, the problem of adapting such models is that we have to somehow limit the number of entering particles because, like as was mentioned in the talk of Anastasiia, attention is compute and memory hungry. And when we have basically unbound inputs and the models that were originally trained for like sequences of up to 130 inputs, we cannot just feed them like a sequence of 1300 inputs because it will require 100 times more compute and memory. Question number 2 is whether or not we can use graph-based representations to improve the results. We hypothesize that we can because graph-based representations were used quite a lot since 2020 in the problems of jet tagging. We can represent particles as basically point clouds and add some edges representing interactions between them. However, our problem is complicated by the fact that most of the particles in our input set are noise. They are not related to the tau leptons. So it is a question whether or not basically attending to them helps us achieve better results. And final question is whether or not incorporating explicit physical constraints can help us with the problem. So, for instance, for the tau lepton, we have invariant mass. We have energy conservation laws. So we know that if our triplet of pions in total has more energy than the tau lepton itself, then it's definitely not what we're looking for. As for the approach, the vision of our solution is a multi-stage pipeline that progressively filters a couple of thousand particle threads down to a single triplet of pions and operates where the standard methods fail and eventually where even the low PT methods fail. To achieve that, we have that approach. As I mentioned, it is multi-staged. We start with a relatively simple MLP to filter out the obvious noise particles. We set up a cut of like 600 tracks because in our experimental results it was a number below which we managed to achieve recall escape of over 90%. So we keep 90% of ground truth particles. And then those 600 particles can actually be processed by more powerful algorithms like mentioned particle transformer with attention layers. It's still quite expensive, but it's not prohibitively expensive, like 3,000 particle input sets. the outputs of that second stage refinements are themselves not, let's say, not the exact triplet, but something like 50 to 100 candidate tracks. And at which point we will be able to introduce some combinatorics into the problem, basically to try to iterate over all the possible triplets, filter out those that are not that clearly violate physical constraints, and then restore final triplets, finding out what are the most likely candidates for us. As for the timeline, we had this research plan designed during the winter. It was adjusted quite a bit during the process. For instance, we decided to drop the briefings with the UCH and CMS groups. Instead, we switched them to basically email updates and conversation, plus physics-aware and graph-based models. They were not designed like separately, but even like the stage one model relies on both graph-based and physics-aware concepts to achieve the results that we have now. As for our early results, we first of all secured access to all the computer infrastructure. We set up this training and evaluation infrastructure. We discovered that we need a multi-stage architecture. I spent quite a lot of time trying to do like a one-shot prediction. It did not really work, mostly because like the more advanced algorithms, we cannot apply them to the entire input set, and we cannot easily compress that entire input set because we have very, very weak signal in the track, basically 3 lines out of 1200. It's below like 0.25% of ground truth. We developed and trained the stage one pre-filtering model. It's, as I mentioned, it's like a relatively simple MLP plus KNN layer. I experimented quite a lot with different designs with more advanced graph-based models. They all hit basically the same scaling regardless of the architecture, laws, etc. Our main hypothesis is that due to like the extreme level of noise in the task, it does not really matter how much and how complex our graph-based interactions between particles are, because particles mostly attend to noise and not like ground truth patterns. Yeah, and that's basically the final early result that I can mention here is that local receptor fields are insufficient, basically due to because of the same reason why we cannot use jets. And our conclusions: low-bit regime is challenging. That's why it's basically a master's project and not like a small research investigation. We managed to we proposed a multi-stage pipeline to filter down a lot of tracks into just a few. We completed stage one and currently working on stage two with like attention transformers, etc. And our main work here is to complete stage two and implement more physics-aware, more physics-constrained triplet selection stage, and finally evaluate everything end-to-end on the cluster of CMS. And that's it. Thank you.
Thank you very much. Do you have questions? Well, PT, tau, leptons, whatever clusters, high energies, low energies. No questions? Yeah, I have a practical question.
Mm-hmm.
Why do people need this stuff to know about?
Well, mostly there are two main experiments that will benefit from better reconstruction quality of such low PD particles. First is about investigation of mesons. Those are another type of particles. Those are another type of particles that researchers at CERN are currently interested about. I'm not very familiar with that kind of experiment. The second one is about dark matter search.
Mm-hmm.
So knowing like the characteristics of more noisy, more common particle allows us to understand better like what dark matter is, how it is originated, why it is there in general.
Okay, thank you. No? No more invented questions? I have a second one, if you don't mind. But this is even more practical. If we look at your stage 3, which looks like the definitive one, because you arrive at just as triple. What happens if the first stage worked fine, the second stage worked fine, and here you fail miserably? How do you mitigate the risk in your master project?
Well, as you mentioned during the academic writing course, master's projects are not like research papers, and we are allowed to fail some experiments there. Even having like 2 stages that filter out the input side of like 1200 particles into, I would say, below 50, we would be able to develop on those 50 particles later to build like some more powerful models or some better like filtering capabilities, or just to take the output of those 2 stages and input them into the existing model. That would definitely, I mean, this in the production grade model that is currently used in CMS, it would definitely benefit from having to source through fewer noise particles.
That was a very opportunistic answer. Thank you very much. I would rather say that this is in fact comparable to the current solution. And this, if implemented, and there are good signs that this will be implemented as far as I understood it, this will be an improvement already, isn't it?
Yes, I mean, it will be. I would say that they're not like directly. It's not like an apples to apples comparison. The existing model it produces like a limited set of triplets of pions, and usually from the discussions with researchers that are using those models, about like every 5th triplet is correct. So they're basically and tuning them, checking if what the model outputs makes sense. Stage 2 will not be able to produce like triplets yet. It just like it just filters out a lot of noise.
Okay.
Yeah, and then suggest what pions we should take a closer look at.
Yeah, that will be the last question.
Will you be allowed to visit the collider in case it's successfully developed?
I mean, problem is I'm going to see LP result, so not sure about it yet.
I can answer this question. Everybody's allowed to visit the collider. There were times in my life when I crossed the collider by train every day, 2 times per day. So no problem. The airplanes cross the collider. So thank you very much. Our next speaker, our next speaker is Shandra, supported by Milos Cernak. They will be talking about psycho-acoustic functions for neural speech enhancement. So, Yuliia, the floor is yours. Please go ahead and now to the session.
Yeah, so the topic of my research is using psychoacoustic loss functions for in neural speech enhancements, and using one particular matrix, Zinterly, for training those speech enhancement models. So I will start with motivation. Why standard losses like more not fail, but why they do not give such good results. About background, what is Zinterly, about what kind of research questions we have developed, about the approach, about early experiments, and some steps about what we have done after the article was submitted. And why psychoacoustic loss? And so standard losses like mean squared errors or some spectral losses, they usually treat audio or spectrograms like mathematical functions, and they are calculating what they are doing. And as humans, we hear differently, and it's for example, differences in loudness are perceived not like differences on logarithmic scales. Some frequencies are perceived better, some worse, and differences. Research topics here, like there are psychoacoustic metrics that I used to estimate speech quality. And there are approaches that are to use those metrics in training neural networks, but they have their challenges, like differentiality, slow training, or you need a complex adversarial setup to train them. And why we wanted to try is interesting. This is psychoacoustic metrics that has a very high correlation with human perception. And it works like this. You have in the pipeline, you have a reference and clean audio, and you are computing distance between them. And it consists of several stages. First one is a phasor filter bank based on equivalent rectangular bandwidth features. It's a simulation of how human ear is processing the sound. And then resonator, energy downsampling, quite big if you compare it to fast Fourier transform. And rescaling, dynamic time wrapping alignment, and nearest similarity distance computation. As an output, we have a number from 0 to 1, saying whether those audios are close or not. And the questions that we were working on first, constantly, we need differentiable and maintaining the same accuracy as original metric, which was proved to have a high correlation. Second question, will it be actually beneficial to use this metric? Will it be better than other losses? And the third question, whether it will be practical to train networks with this loss. And hypotheses are that if we will take this psychoacoustic matrix, it should be better than signal level losses. And the second hypothesis is that we will be able to use auto differentiation for very compute heavy and sequential code. And the second hypothesis is that we will not use those basic-based gradients. We will be able to use them just as without any adversarial training, just as loss. And what we were doing here. So as a first iteration, this metric is in C++, and it's quite efficient, but trying to meet two things. Being integratable into their training pipelines, which are usually PyTorch. And second thing, we need to have gradients. So the first iteration was to check whether pure PyTorch porting will do the thing. And there were some non-differentiable operators that needed to be replaced. For example, some small replacements that are handled by PyTorch easily. Then there's this direct time wrapping needed to be replaced by other algorithms, and just check it. And the problem with it that this filter bounce that is implemented in the fast pipeline is infinite impulse response filter, which means that you are having a flow of samples, and every other sample depends on the previous one. So this is highly sequential algorithm, and it is very, very slow, like impractical for training, even on a small data set. That's why this first iteration in the was used for any training because it's so slow that you cannot attach much with anything. And as a second approach, where it was developed is a hybrid implementation. So C++ code is fast, but we don't have a auto differentiation, which PyTorch does for us. So the approach is to use forward pass as a C++ function and then use LLVM compiler plugin that works on compiled C++ code and allows you to do auto differentiation on C++ code. And this was kind of a combined system, which had some parts of C++, some parts of PyTorch, and was working together. And it made the training feasible. It was 16 times faster than PyTorch, with a good approximation for this filter bank. But the downside was that it required multi CPU machines and GPU, which is not that frequently you can find those. And here in this implementation, if you are processing batch, it was parallelized. Batch processing was parallelized, and if you have bigger batches, you need to do sub batches because to make one sample okay. And experiment for this, for first experimental setup, we're a simple net, nothing special in gets an input to magnitude spectrogram and outputs multiplicative mask. Data set quite standard and small voice band demand. And training with this setup was slower, but for the matter of experimentation, it was okay. And for this phase, interleaved metric show good achievements on that set and voice band demand, which at least shows us that our metric is good enough to continue experimentation. And by conclusions we have is that interleaved can be differentiable and can help in learning. It outperforms mean squared errors metric, which is quite trivial, but at least we have our sanity check, and it's feasible for using in training. What were the next updates since article was submission? We have dropped direct time wrapping. By analyzing errors, we have seen that there were a lot of incorrect alignments for higher signal to noise ratio, and usually for speech enhancement we can do that because the data sets are already aligned. So we are replaced it with diagonal alignment. The second very important difference is that infinite response filters were replaced by finite response filter bank that were calculated with ATPs and so on, and it allowed to move the magic fully on GPU and drop the CPU pipeline, which complicated finding good machines for training. And done some other experiments with complex spectrogram. Yeah. Also, I think I can mostly, yeah, I can mostly. So those experiments were not also showing some result, but not that successful. But we will be dropping them. We will not be developing what is going on with this network, because as a next step, we will have a training on our state-of-the-art models. So this is also still toy network to develop. And now we are working on comparison with other perceptual losses, because actually it's not the only one that is working, that is mimicking human hearing. And we need to understand whether it's better or not for those perceptual losses. And the second thing that we're working right now is working with sort architectures for speech enhancement, and to see if we know good baselines metrics for those architectures, and we would like to see if adding is interleaved to the loss stack will be beneficial for them. And yeah, so what we have achieved so far, we have a differentiable version. It runs on GPU, and it gives some improvement, and we know that network can learn. And next steps will be in priorities. This is training, fine-tuning sort architectures, evaluation on diverse data sets, non-sim data, and for the best model, we will need to do subjective evaluation. Subjective evaluation is a process of estimating audio quality when actually people are listening to different audio samples and rating them. And based on the protocol, it's a different rating schemes, right? So they are comparing two audios or with several. Yeah, I guess yeah, I also stop a little bit here because I have received a comment from a reviewer about not covering fully these parallelizations that I have done for making my pipeline to work, and clarification on this LLVM compiler permissions. It was I haven't I haven't added any theory about that because it was not a research contribution. It was kind of a tool like for loops and so on, just to make it running. Yeah, it solved the problem. Yeah, that's it. Thank you.
Yeah, perfect no time. Thank you. And do we have questions? We have 5 lovely minutes for questions. Please go ahead.
So what does the term psychoacoustic means actually? So is it about how our air biologically hears, or is it about something that's happening inside our brain from signal level in Milos and so on?
So it is about how our ear is hearing. First of all, it's based on how people perceive actual frequencies. Some frequencies are better for perception, some more worse. It emulates this tympanic resonator. This energy sampling is also they have calculated this kind of neural oscillation rate. So it is a physics of an ear. So.
Great. Thanks.
More questions?
Well, I just found out that your scientific advisor is an author of this.
Yeah, he helped. He helped to evaluate it.
Interesting. Yes. So my question: do I understand correctly that this metric implementation C++ it's pretty recent? Because I don't understand like why nobody made it differentiable yet. So like you are probably one of the first, maybe somebody is doing it already in parallel, but so why?
Yeah, it's pretty recent. I think they have published an archive paper in November, something like that. But as you said, my supervisor knew about it earlier because he helped to do evaluation from one point of view of audio quality for this for those people who developed actual methods.
Okay. Thank you. Our next speaker. Speaker is Stanislav. Hello. Well, tell us about hardware accelerated worst is optimal joints for better margin. Stanislav, and the floor is yours.
Okay, hello everyone. Today I will talk about hardware accelerated worst case optimal joints for graph pattern matching. This work has been advised by Yuriy. So the plan is the next. First of all, we cover some motivation and background. We'll explore some of related papers important for our work. We review research questions and methodology. I'll present the evaluation plan, early results, and some architectural design, and we'll conclude everything there. So first of all, what is graph pattern matching in general? So suppose we have data graph G, and we want to find all the subgraphs that look like Q1, Q2, and Q3. So basically, graph pattern matching finds all subgraphs in data graph that are isomorphic to a given query shape. This is for operation in fraud detection, in social network analysis, graph mining, etc. Even a simple patterns like triangles or forked leaves can require examining large portions of the graph. And usually in databases, such pattern matching is performed via joins. And basically, most of the databases performed via binary joins. So where we want to, if you want to join 3 tables, we perform join on the first pair and then join the last one. And all the optimization effort is concentrated around choosing what the order of the tables we should perform these joins in. But for cyclic queries, there is another problem. So this intermediate table that comes out from table R and from join table R to table T can blow up and create up to m² temporary tuples. But worst case optimal joins, basically it's recent family of algorithms, and they overcome this by merging all n tables together at the same time. Yeah, by doing this, we can avoid materializing large pairwise intermediates. So coming to the practical implementation, the first one, which is implemented in several databases, is called leapfrog join. It uses sorted tries for for representation of the graph data, and which is maps naturally to CSR style adjustments lists. At each level of depth of this tries, leapfrog join intersects the relevant candidate list and backtracks over the intersection tree. The next notable work is called empty-headed, is a relational graph engine that basically brings it to another level. It is pretty old, developed in 2016, and they basically accelerated this empty-headed leapfrog join with SSE instructions, and added a couple more tweaks to the algorithm itself. They reported up to 3 orders of magnitude speed up over high-level engines and 10x over low-level baselines for graph pattern queries. And here is the next work that was presented last year, which brings leapfrog join to the next level, and they come up with a way to execute the whole process completely on the GPU. They presented labeled grid format that partitions data by source and destination ranges and avoids flooding irrelevant regions. Their implementation works great for the large graphs, but for the small ones, the performance is suboptimal. So there are a lot more of implementations over the last years. but only there is only a couple of implementations that are integrated to real production database systems. Most of these are research prototypes, that have no practical integration as we. So from coming to the research gaps we identified. So first of all, CMD inside worst case optimal joins have been explored almost a decade ago. And a public, there is only there are no public AVX 512 implementations from the list we have evaluated. In related work, backends have been primarily evaluated in isolation. So it's unclear how do they compare in the same conditions, and it's still not really clear how does repair specific backends can improve worst case optimal joins on the end-to-end graph or codes inside database management systems. That brings us to the research questions. So first of all, research question one is how do scalar IVX 512 and GPU backends compare to the standard sorted set intersection? What speedups do remain after integration to database management system, and which workload properties should determine when to use scalar, CMD, or GPU execution? Our research methodology is next. For research, we've chosen DuckDB, stack PGP extension because of its modular architecture and open source code base, and active community, research community as well. The methodology, we split the whole project into two phases. So first, we implemented our custom intersection backends accelerated with AVX and CUDA over CSR format with adjustment lists. And in the next phase, we are planning to integrate our prototype into DuckDB and measure the results. We will perform experiments with varying list sizes, skewed data distributions, and element widths, and measure transfer overhead. So our evaluation plan is the next. So we created kernel benchmark to measure throughput latency and speedup for adjustments to list of sizes 10 to 10 million, and we perform end-to-end evaluation. We will perform end-to-end evaluation of site data cyclic and mixed graph pattern queries with DuckDB and PGP. And solution will be evaluated using two benchmarks: LSTB, which is an industry standard benchmark for pattern matching queries, and LDBC social network benchmark, which gives us more natural workloads for the database management system. Results will be compared against scalar execution and unmodified DuckDB, DuckPGQ version, and Neo4j. So we are targeting the following architectural design. So we have some query processing later, and we are going to develop LFTG framework, which will be able to handle the workload with using one of the backends, and each of them can have their custom data layout there. Coming to the early results, we developed several prototypes. So first of all, we are ready to present one of them, this triangle counting in memory prototype for CPU AVX and CUDA backends. AVX 512 is empty-headed inspired, has empty-headed inspired layout. This implementation currently gives us the best overall performance for the real graphs. It even gives better performance than CUDA backend, as it doesn't have the PCIe boundaries problems and PCIe latency. Coming to the synthetic graphs, AVX 512 also stays the fastest, up to 4.5 million edges. And then CUDA is faster. Currently with what we accomplished is literature review engine selection. We've developed scalar baseline and benchmarks. For our project, we're working on the finishing SIMD and GPU implementation, and we work on engine integration and analysis of the results. So, discussing the risks, we have two categories of risks. Talking about performance risks. GPU, we have several of them. First of all, it's GPU kernel launch overhead, which effects of it we've already seen. That for really small graphs, like GPU is overkill and doesn't perform so well. The second problem is PCIe transfer costs, and it can limit end-to-end GPU soup. And some power law degree distributions can cause load imbalance across the threads or bars. So this is usually mitigated by partition, selective transfers, and dynamic scheduling. These techniques were already evaluated in previous work as successful. There is also a scope risk if the integration is more complex than we expect. We are planning to fall back and present only GPU backend on the kernel, evaluated on the kernel level only, while preserving the cross-backend comparison and SSL content contributions. To conclude, this project addresses three concrete gaps. So first, modern CMD evaluation, fair cross-backend comparison, and end-to-end validation inside the production system. Our expected outputs include AVX 512 and CUDA backends and unified benchmark suite, along with practical crossover deadlines. We will perform correctness checks against our scalar baseline, and all the code benchmark suite and correctness tests will be released and as an open research artifacts. That's it. Thank you.
Thank you very much. Last bunch of questions, please. Coffee follows.
Everyone wants to.
That's a motivation from my side. But Rostar, you didn't want coffee? Okay. Let me ask a provocative question. Would you allow me?
Okay.
No consequences. You're a big guy. So looks like more like engineering work. Is there any scientific novelty in this project?
So that's a great question, frankly speaking. So currently, most of the worst case optimal join efforts are in the research field. So they are, we are primarily targeting to bring it to the state where they can outperform consistently the binary join algorithm. So for as to scientific contribution, probably evaluating on a new hardware like Waves 512 is one of the possible scientific contributions, because as I mentioned, there is almost a decade-old implementation, and that brings that's not just we take your instruction, your CPU, and it works as expected. No, because for example, Waves 512 has throttling problem, and we probably have to come up with different ways to leverage that power. And probably it might end up with some algorithmic contribution to the computer science field.
What would be your contribution to the research community in the field?
Sorry?
What is your planned research contribution or an offer to a research community in the field, except you open source this? Do you plan a sort of a benchmark? So different hardware?
Basically, we are evaluating, we want to find, as I mentioned, the crossover where CPU meets GPU, where how to evaluate in your systems such crossover point. Basically we give tools to other research community to do that. That's mostly like that.
Okay, I'm done. No more questions? Okay, thank you. Copy that. Even for those who didn't want questions.